So today we'll be talking about on-demand container loading in AWS Lambda. A paper presented at ATC 2023 and about the system which was developed by Amazon uh, back in the days, like about like 10 years ago. And basically they are talking about their optimization approaches to the storage system, which allow them to optimize the data movement problem and allow them to spawn, for example, the containers at speed of 15,000 per second per customer. And at the same time, keep their goals about the tail latencies close to their targets, which are 50 milliseconds at the call starts. So yeah, if you want, you have all the links here anyway. And the paper was basically the work presented by one of the authors, Marc Brooker, and they use like in this video basically, and he generally gives a high level overview of what they did. And it's pretty good, but we will be more strictly following the chapters of the paper and give some estimations that they did mention. And also I think he skipped just a few pieces, like multimodality, for example, of their cache solution, which we will show, and that is part of the paper. So with that, this is the abstract of the paper. As I said, AWS Lambda is a function as a service system. It's basically, you can think of it as a Docker that where you can upload the image with your code to the provider. In our case, it's Amazon, and then Amazon will enormously scale it out for you, like really fast if you need it. Like, so you can have to like an ability to pay as you go, and just have all the scalability advantages of the serverless solutions, which is very convenient for some scenarios. So when they start, their system basically allowed on the images of, if I recall correctly, 15 megabytes, and then they moved to 250 megabytes. And after those optimizations that they show in this paper, and this paper is basically about the engineering approach to the optimizations problems in their system, they were capable of now spawning 15K lambda per second per customer functions, right? And then with the huge aggregate RPS, and at the same time with all the latency goals that they have. And yeah, and the image sizes grew up to 10 gigabytes, which is like super much. Let's say much. Yeah, and the paper is about the storage and caching system that allowed them to do all that. So let's start with a small estimation about the size of the system that they're talking about. They're mentioning that they have like trillions of requests per second in the last 8 years, and serving like millions of requests per second all the time, like every day. And yeah, we can quickly calculate that the cluster size is about at least 20,000 nodes without considering the IO. That we can assume that most of the time, for example, at least lambdas are downloading from internet and only then make calculations and the uploads the result. Like, so if we'll take in consideration the speed at which they are capable of spawning containers with 15,000 thing and the image size, we can quickly estimate that the required network bandwidth for moving all the containers images to the workers is 150 bit per second, which is super much. And yeah, the question was how to solve this problem and allow this to be a reality. Yeah. That's what they did. Basically, sorry. Yeah. The problem is that we can't basically just move all the images to the workers fast if we want to spawn at that speed. So we can exploit the idea that actually when the programs start, they don't need actually all the files and the data that is present in the images instantly at the moment of its start. This is one factor. Another factor is that the images, like in the world of Docker Kubernetes, for example, they usually consist of layers, and in most cases, those layers are identical in very, like, most of in the most of the images that they and the workloads that they are having in their system. So basically, the thing is that those images that the users are upload for Lambda functions, they can be cached because they are very common, consist of the blocks that are very common both horizontally and vertically. And the idea was that they can exploit this, I think. And then they somewhere calculating or showing up that, yeah, I think in the deduplication part, that overall in the whole system, they have only 1% of unique blocks among all of the data, the images that the users are uploading to the system. And the paper starts with an overview of the architecture of the Lambda system and the walk path. And the walk path looks like that. We are having a user request that are hitting stateless load balancer that then loads the metadata from let's say a database. It loads the metadata about the function that wants or needed to be invoked, right? Then it does authorization and authentication, and then asks for a slot, for capacity slot reservation in the worker manager that is a stateful service already. And when this slot is allocated, the work actually goes to the worker where it actually executes. And the worker is represented as a micro VM that runs on top of the KVM with the help of Firecracker. And on top of the Firecracker, they have a Linux guest kernel with a shim that allows basically the runtime that executes customers code. And this tuple, Firecracker, Linux, and the shim is the unit of isolation for the Lambda service for a single call, so that everything is very nicely isolated. And yeah, and as I said, the first iteration of the system allowed only the images of really small sizes of up to 250 megabytes. And even then, with 10 gigabits network, it takes a lot of time to download the zip archive of the image to your worker. And then you also need to unpack it first to start loading code into the memory, which takes a lot of time, and it doesn't match their goal with 50 millisecond cold starts. So the new system that they invented basically looks like that, and explored those three things about cacheability and sparsity that I mentioned before. And the idea is that, first of all, they could do here a couple of things. Like, first, don't spend storage space for storing the same data, which is obvious, right? So they needed somehow to implement deduplication. And the deduplication, of course, somewhat is a bit of a problem, because you also want to have blocks or chunks of your images encrypted. So for that they just went with a deterministic encryption, which is really nice, elegant solution. And the second thing is this latency and huge images problem. The idea was that they can, first of all, move to loading blocks lazily, and then do not load the data they don't need right now. And then they did this 3-tiered cache thing, which efficiently caching blocks or chunks of the image for the Lambda workers. And it has a really high hit rate such that they basically meeting their latency goal. So the system works like that. The customer uploads the image to the container registry. This is the top left square that you can see. Then the system encrypts, it first flattens the image by collapsing all the overlay FS layers into a single layer. So that then they can cut it into chunks, encrypt, and deduplicate. The thing is that it's not very simple to do deterministically, so they have to write their own patched version of the file system that allow them to do a deterministic collapsing of those image layers. So this is the first thing. Then when they collapse it and flatten the image, they cut it into chunks of 512 kilobytes, which is basically, I think it's the corresponds to the block size of the modern SSD disks. So they cut it into chunks in a way, specifically in the way that the same chunks of basically the same files pieces they had the same content, right? So they then encrypt it deterministically so that each chunk that has the same content will have equally identical binary representation after the encryption. So then they could upload it to the reliable storage, which is basically an S3. And they using specific names to do the deduplication at the same time. So that they are uploading only the chunks that are missing in the storage, which is super convenient, right? And then from the S3, it already can be loaded by the intermediate cache layers in front of the block device that is then mapped to the firecracker, and then from there it's mapped to the final Linux guest kernel. So at the micro VM level, it looks like that. They have a local agent which resides near the firecracker, and it provides the firecracker with a fuse mapped block device over the virt.io interface, and then from firecracker it mapped to the guest kernel as a block. I'm not sure. Maybe I'm wrong. Maybe the fuse is at the next level, but I'm sure. So anyway, mapped to the guest Linux kernel. So the customer code sees the completely fair disk device, but it underneath it actually lazily loads and blocks, which when it wants to do that, those requests that turn out into the block request, they goes through all of these layers of Linux kernel, then firecracker virtual block layer, and then the fuse somewhere also, then back to this local agent, which is, as far as I'm actually, which then translates it to the local worker cache, which stores loaded blocks from the other layers of the cache system. And also it maintains the list of the blocks that are already loaded with the help of bitmap index, and also supports blocks overlay thing to be able to allow the end user system to write to the blocks, and at the same time allow other workers in the machine to share the loaded blocks. So yeah, basically that's how it's implemented right now. And then in the end of the paper, they mentioned that they actually trying to move away from the fuse block device, because like this organization that they did requires a synchronization of 4 different threads in the different layers, and it turns out into the huge overhead engineering onto the load, and then also has the overhead of lots of context switches that are happening because of the cross boundaries passing. There's something in the chat which I can't probably read. Oh yeah, I see. Okay. So the deduplication. Yeah, they show this graph and estimations about the amount of chunks and their means about the data, and this is how they calculated the storage win for the deduplication. So yeah, I think Marc said that overall it's about 1% actually of just unique chunks. So yeah, we just going past it. Yeah, and then the convergent encryption. Convergent encryption is a way to encrypt data such that all the data will be identical after the encryption, so that the encryption blocks are identical if the data was identical. And it allows them to do the deduplication first, and then also efficient garbage collection, which is very nice property, right? And also, I would say that also the approach that we picked is also very interesting. I mean, not interesting. It's like it has another nice property that, yeah, let's say, I just like that idea that the keys are deterministically derived from the data pieces. Like it's really convenient that they, yeah, not generate randomly, but yeah. So anyway, so when they flattened the image into a single layer, they cut it into chunks and then encrypt it in the following way. They basically take the SHA-256 hash of the block or of the chunk with a salt, but it's not very important that they have a salt. So they basically hash the content of the chunk, and then it's the key for encryption. And then they encrypt it with the IS-CTR algorithm with a fourth component, all equals 0 to be deterministic. And basically that's it. So they derived the key from the content of the chunk. And then the chunk ID will be probably a hash of the encrypted chunk. And it's enough even already to upload it to the S3, do all the deduplication work, which is very cool thing. The manifests for the images, they consist of some data. The list of those IDs of the chunks that reside in the image, right? Because they have to have an ID to load them from the backend storage, and also the actually keys for decryption of those chunks, and which are basically, as we remember, derived from the hash of those chunks. And yeah, the only part of the manifest that is encrypted is this list of the keys to decrypt the chunks. And also the whole manifest is signed with something like HMAC thing, so that you can just replace some chunk in the middle and do no one. Yeah, whatever. My English is not enough to say that. So the garbage collection then. So they do encryption, deduplication, nice, everything works. For garbage collection, they don't do usual graph traversing. They just create a new namespace once in a while, and then copies all the data that is in use there, and then retire slowly the old namespace. That's basically the whole idea. The only thing is that they retire it slowly, such that like the code has still an access to read, an ability to read the chunks from, for example, the old namespace if they're missing some way, do the bugs, for example, in the new namespace. But then they shut out about that really hard because it shouldn't happen normally. So like this is how they're trying to safely garbage collect unneeded images. I think nothing pretty much interesting there. So this graph basically shows the distribution of chunks among the different tiers of their cache system. And the most interesting thing here, I think, is that they have 99.9% hit rate in their cache at the second layer. So it's all like most of the time it isn't hitting S3 as I understand. And 65% of the local cache hit, which is pretty impressive. Also, small details are that the second level cache layer, which is not local, which is AZ, availability zone level local, it consists of two actually caches in memory level and disk layer caches. And for eviction, they use a K algorithm and serve blocks over the HTTP2 protocol. Tail latency design. They were thinking about how to improve tail latency in this intermediate level of the cache. So they basically to improve this cumulative density function, as you can see on the right slide, on the right part of the slide, in between the blue and the red lines. They designed this AZ level cache in a way that it's using erasure coding to return the blocks that customers are loading, so that they have this effect of on the CDF function just in comparison to parallel requests. And at the same time, that's what allows them to provide redundancy in that part of the system. Really impressive design, I would say. So then they were thinking about the metastability effects in their system, because as you just saw, the cache hit rate is really high, and if it will fail some way, it will result in 500 traffic increase times to the S3 backend. And they, of course, saying that the S3 will be easily handle all that load that would suddenly appear on top of that. But at the same time, it will lead to redistribution of the load in the whole system and may lead to metastability failures. And nobody wants that. So they basically what they did, they limit concurrency levels of this system on high levels of abstraction, and also they do tests of cold start thing regularly. Here, they were also mentioning an interesting thing that how the failure propagates. Actually, that the failure of the cache will result into that the functions will start loading and working much more slower, and that will result in a fast lack of the free slots for workers, and then there will be like lack of all the other resources in the system. So that's why they just had to limit the concurrency. The cache eviction, as I said, the cache eviction is okay. The sizing they're saying they're using 5 minutes rule. The 5 minutes rule is the rule that says that basically the cost of cache retention should be equal to the cost of loading the data from the backend storage. But I think if I'm not wrong, in easy words, it's just basically you need in the cache the amount of data the users consuming in the last 5 minutes in a with a goal in mind that you must hit your performance targets. And they basically what they're doing, like a total cache size must be larger than needed to achieve the hit rate and optimization costs. So the production experience views work pretty much well. Local agent written, yeah, everything is written in Rust, and Rust works pretty fine. And they like the success S3 teams had with Rust, and they also really appreciate the with victorization thing that the Rust compiler has. They are unhappy that it's very sensitive with performance optimization and to be sure they doing micro benchmarks. Then they also show that they have the multi-modality latency thing in their CDF latency function. As you can see here, yeah, they mention also here that the memory tier is 10%. And yeah, and they mentioned this multimodality appears because of the write back effects of the cache host. Yeah, another lot about latency. The fuse, as I said, they somewhat are unhappy about the jitter that it has because of the spread of the because it has just a lot of layers over which they had to pass the block loading writing requests. So they are moving to user fault FDM map instead of the Virtio block device and the fuse. And yeah, the related work is that they are looking forward into other options for optimizations. And now, like, there are lots of systems that have the common problems and they are looking into their experience too. So in the conclusion, they build a storage with cache where they exploit the duplication ratio OMT caching, user-based file system conversion encryption to make so their performance goals reality. And I think, yeah, this is it. This looks, yeah. The analysis. I think that this is normal engineering work, which maybe, I don't know, my work is similar to what they're doing, and maybe others engineers work similar also to what they're doing. At least it seemed to me when I was reading that how it works look like. Yeah, that's it. It's the last slide. Pretty impressive and elegant combination of different solutions.